Okay, so we now need to familiarize ourselves with two very important definitions in metric spaces. And the first of these two is in regards to the notion of open and closed balls. Okay, so we define an open ball in Rk about a given point x in Rk and of some radius r greater than 0 as being the set of points y in Rk for which the distance between x and y is less than r. And for closed balls we similarly define it, except that that distance may be less than or equal to r. Now, for the second definition that's also very important is in regards to convex sets. And we say that a set E, a subset of Rk, is convex if essentially for any 2 points within the set E, every point that lies on a straight line joining the 2 points x and y in E is also a point within the set E itself. And so the way we can mathematically express that is to say, okay, if we have for any 2 points x and y in E, and for any scalar or real number between 0 and 1, we'll find that lambda x plus 1 minus y times y is in E itself. Well, it's relatively straightforward to prove that balls are in fact convex. So if we take any 2 points, y and z, within a ball of some radius r centered on x, then obviously y and z by definition satisfy the following inequalities. We find that okay, so we say let y and z be in our ball of radius r centered on x. Then clearly y minus x is less than r and z minus x is less than r. We want to show that this set is indeed convex, so that is that any point along a line joining y and z also lies within our ball itself. So if we define w as being lambda y plus 1 minus lambda z, then we now need to show that that the distance between w and x is also less than r. That way we've shown it's also within the ball itself. Okay, so we now find lambda y plus 1 minus lambda z minus x as equal to lambda times y minus x plus 1 minus lambda z minus x. So this is just grouping the terms together, and of course from the triangle inequality we know that this immediately follows. Okay, now here's the part where we just use the fact that y and z lie within the ball. So the absolute value of y minus x and the absolute value of z minus x are both less than r. So we have that this whole expression on the right hand side as being less than lambda times r plus 1 minus lambda times r, which is of course equal to r itself. So this proves that balls are convex.